Hey, hello everyone. So, welcome to today's stream for contest discussion of Codeforces Round 1069. So, let's start with the first problem first. So, the problem says that Little Fairy has a ribbon with 10 to the power 18 cells and an infinite variety of colors. The first n cells of ribbons have already been colored, where the ith cell is colored with color AI. Now Little Fairy will color the remaining cells in order from n plus 1 to 10 to the power 18. And what is the criteria of coloring? Little Fairy will count the number of distinct colors currently present in the ribbon, denoted as Ci. Then she will color the ith cell with color Ci. Okay, so the number of distinct colors currently present is inserted as the new number. Okay, so let's say we have some numbers. All right. So what will uh, little fairy do? She will count the number of unique elements. Let's say here we had three ones and two twos. So number of unique elements is equal to 2. So she will insert that particular number inside the array. All right. So she inserted 2. After inserting this number, so there can be two cases. All right. The new inserted can be a part of array. The first case is part of array. Second case is not a part of array. Alright. So what happens when this new inserted number is a part of array? The number of unique elements remain same. Alright. Because the number was already a part of array, only its frequency increases, not its count. Only its frequency increases, no new number is added. Now, if what it was not a part of array, then the value of Ci changes. The Ci is denoted as number of unique elements, because one new element is added, Ci changes. So a new Ci will continue forward. Let's say what happens in the first case when the number of unique elements remains same. In the next step also, the uh, number of unique elements in the next step also, Ci remains same. Since the value of Ci remains same in the next step as well, this process will continue. That is, the new number is a part of array, and the number of unique elements is same. So again, Ci will be inserted, and this will happen how many times? 10 to the power 18 times. All right. So this tells us that last number was Ci itself. Now, the second case. If this Ci was not a part of array, if this Ci was not a part of array, then Ci changes. Alright, and how do Ci changes? Ci plus equal to 1. So, what is the upper bound on number of operations that we need to do so that one of the first operation, that is the value of Ci is a part of array operation, is done. Alright, what is the initial value of Ci? Initial value of Ci. It is from 1 to n, because there can be at most n unique elements. Alright, so the first new inserted element will be from 1 to n. Now, if n is a part of array, then the first condition is satisfied, and we need not make any further loop. Alright, let's analyze the first case. In the first case, if all unique element, then Ci equals to n. Alright, and what is the high upper bound on the value of AI? AI is up till 1e3, 10 to the power 3. Alright, now we find the initial value of Ci, that is the number of unique elements currently, and we keep on increasing it. Okay, we are discussing the algorithm now. We can find the initial value of Ci and keep on increasing until we find at least one known element. The known element is the element of our array itself. So at most, how many number of iterations will be needed for this? Because the upper bound on the value of AI is 1e3. We can do this in at most 1e3 operations. Alright, so our computations would for sure work in this scenario, because t is 500 and 500 into 1e3 is 5e5, which is very much computable in 1 second. So let's go and implement what we just devised. So initially we have n and a vector. Let's create a map to find the element and to get the initial value of Ci. Now find the initial value of Ci. It is equal to number of unique elements, which is map size. Now while 1, what is the condition for this loop to break? If we can find that element, current element is found, then break, else cur plus plus. At the end, just print cur. This is it. Now let's move to the second problem. So in this problem, we are given three integers n, l, and r. Now we need to construct an array A of positive integers such that the bitwise XOR value from each range x to y should ensure this particular function. That is, the bitwise OR for range x to y is equal to 0 if and only if L is equal to R and y is equal to, sorry, L is x is equal to L and y is equal to R. Else, even if y is R but x is not L, or y is x is L but y is not R, and every other scenario, the bitwise OR is non-zero. So what do we want? We want zeros OR for a particular given range, and for rest of the ranges we want ZOR to be non-zero. Okay, let's move forward to some known facts about ZOR. Known formulas. The first formula is A XOR with A gives 0. Second formula is A XOR with 0 gives A. Now, now let's move forward to how we would devise a plan where the range L to R gives XOR 0 while other do not. Alright, that is the requirement of the problem. So using these two methods, we need to devise it. Let's say we are at some range L to R. Alright. So when would this particular range, let's analyze it this using prefix of source. Alright. Why? Because if we want to know, okay, there is a very famous problem of uh, how to find a element, okay, how to find a range ending at R with XOR 0. Okay, if you want to solve this particular problem, this particular subproblem, what would it say? That the XOR of range L to R is equal to 0. That is, if we had, let's say we have some numbers 1, 2, up till L minus 1, then from R plus 1 up till N. Now, if we keep on taking XORs up till L minus 1. Alright, let's say we are just iterating and taking XOR of every particular number. Then we are here, we can say that as prefix of XOR. Alright, prefix XOR of L minus 1 will be present here. Now, from L to R, we know that XOR is equal to 0. So, we know that E XOR 0 is equal to A. Then it is guaranteed that prefix of L minus 1 is the same value present at R. Alright, in the prefix, according to this particular formula. So, what do we observe from this particular scenario? If we keep prefix XOR, then the indices having same XOR are the ranges that gives XOR 0. Alright. So how can we solve this particular question using this observation? So if we observe, then prefix XOR prefix XOR must be unique for each indices. Why? Because if there is a repeating prefix XOR, then that means that range of XOR of that particular range gives the XOR 0. While prefix of R must be same as prefix of L minus 1. Now let's say okay, one more observation or formula. Okay, we have A and we want some number, let's say X, which gives our XOR as B. Alright. So, we want that a number should exist which is equal to X, and A XOR X is equal to B, and we want to find that particular X. So our X will be equal to A XOR B. Alright. So now what do we need to do? We need to ensure that all prefix are unique, or let's say in increasing order. Alright. Maybe from 1 to n, and only prefix of R must be equal to prefix of L minus 1. And how can we do? We can do using this particular formula. So let's move to the implementation part and understand how to use these formulas to construct that particular array. So we had N, L, and R. We will create a vector of size n. Let's do one based indexing so we can use prefix XOR properly. Initially assign vector 1 as 1. Similarly, prefix XOR of 1 is equal to 1. Now continue from 2 to n. If I equals R, that is, we want the XOR to be same as uh, XOR at prefix XOR at L minus 1. So what is our target? Our target is prefix XOR at L minus 1. What was the previous value? Previous value was vec at I minus 1. We want to XOR some values in this particular value, so that uh, our prefix is equal to wait a minute. What was the previous value of our prefix XOR? It was equal to prefix at I minus 1. Now we want a number XORing which gives us this target. So using the third formula, it is equal to target XOR with previous value. Now prefix set I is equal to prefix set I minus 1 XOR with this number. Alright. Else part. We just want the XOR to be unique. Let's say it is equal to I itself. So what was the previous value? And what is the target? It is I. So bracket I should be equal to target XORed with previous value. And what is prefix XOR? Prefix XOR is equal to prefix XOR at I minus 1 XORed with bracket I. Alright. This is it. This passes the test cases, and let's move to the next problem. We can see that prefix XOR are unique for each array, which guarantees our solution is correct. Let's see that in the first problem, prefix XOR at 3 equals to prefix XOR at 0. So range 1 to 3 has same XOR while no other element matches. In the second problem, prefix at 3 matches 1 again while rest are same, and we wanted 1 2 3 as XOR 0. Similarly for third problem, uh, prefix at 1 is equal to prefix at 4. So the range 2 to 4 has XOR 0. Alright. Now let's move to the next problem. The next problem says that we got lucky to know all important questions in the world. This time the answer is string S consisting of lowercase English letters only. We want to hide the string. We have another string T consisting of lowercase English letters only. We need to shuffle the letters of T so that string S appears at least once in T as subsequence. Among all the possible reorderings of T consisting S as a subsequence, find the lexicographically smallest. Okay, so what the problem says? Problem says that we have a string S and we want to rearrange string T such that the string T consists S as a subsequence and T is lexicographically smallest. So what is our point of concern? Problem says S should have T, oh sorry, T should have S as a sequence. Alright. Now T should be lexicographically smallest. These are the constraints. So what is the criteria for answer to exist? Initially as well, S should be made using elements of T. Alright. How is this possible? Every element in S T should have, or every character in T, frequency greater than its frequency in S. Alright. Else, if this particular condition is not satisfied, then answer is impossible. Now what about when the answer is possible? When the answer is possible, we can separate out all the elements that are required to make T, that are required to make S from T, and then the rest of the elements are uh, arranged in ascending order because they are not required to make T, because they are not required to make S from T. All right. The rest of elements are arranged in ascending order, and the remaining are inserted so that the answer is lexicographically smallest. What do this mean? This particular sentence mean? Let's say we have S as ABC and T as, let's say, BB, CC, AA, DD. Then we need to remove out these 1A, 1B, and 1C from T. Then T becomes B, C, A, DD. Now for the rest of the elements of T, uh, they do not, they are not required to make S as a subsequence. So just arrange them in ascending order. It is A, B, C, D, D. All right. Now insert all the elements of S inside T. How can you do that? Insert in such a way this same particular arrangement of S should be inserted in T such that the arrangement must be lexicographically smallest. Okay, so how can we insert this particular A? The current element of T, it is equal to S. So if we insert this particular element or this particular element, no concern because lexicographically they will be same. Let's say we inserted this particular T. And highlight what we have already inserted. We have inserted this A. Alright. Now we can either insert this B or this A. Inserting this A makes our string lexicographically smallest. So let's insert A again. Now this B and this B, any particular can be inserted because they make our string same. Then insert both of these B, then this C and this C. Same condition, both C's. Then these two D's are left. Insert both of them. So what are the criterias we are following? We are following that use two pointers and insert the string from either S or T which minimizes or makes our string lexicographically smallest. So let's move forward towards the implementation of this problem. So what did we need? We needed two strings S and T. Now create a map now iterate over all the elements of S and remove it. Now, if the criteria for impossible is true, that is, some character is possible which has frequency smaller than the frequency of S, then the value at that particular element will be equal to -1. All right. So move forward towards all of the elements of MP1 Now create another string which we created by removing these elements ABCs from T. How can we make it? Let's say we have temp string. Now if it.ss is smaller than 0, that is there is a negative count, then this means the answer is not possible. In the else part, iterate from 0 to it.ss, and these are the remaining elements, just insert them. This creates our string in ascending order. Alright. Now create two pointers x and y, for one for temp and one for s for insertion. Now create the answer string. Iterate from 0 to the size of required string, that is we want t to be constructed or uh, relocated. So iterate towards its size. If x at if x is smaller than temp dot size and y is smaller than s dot size. If this is the case, then the smaller one will be inserted. Else will push back s at y plus plus. And what if one of them is at its peak? If x is smaller than temp dot size, then answer dot push back temp at x, then x plus plus. In the else part, 1 should remain, so y remains for sure. If all the conditions are false, push s at y plus plus. Then we have our answer array, print it, and this is it. So this was the discussion for today.